Okay, so we're going on to the question 4 here now. So they say visible light, radio waves, X-rays, infrared, gamma radiation, and ultraviolet radiation are types of electromagnetic radiation waves, or electromagnetic waves. Right? So they give you 1, 2, 3, 4, 5, 6. Now they say name the electromagnetic waves in each of the regions labeled A, B, C, D in the electromagnetic spectrum as shown. So you have 1, 2, 3, 4, 5, 6. So that means you just have to use these given electromagnetic waves here and just place it in the box here. Well, you could put it here, right? Like they gave the space for it. Right? So what you need to know is increasing wavelength, right? So you need to know how the wavelength does increase, right? So basically you have you have gamma radiation. So as the wavelength increase, you're gonna have X-rays at A. So you put X-rays, right? And then you would have UV, right? Which is UV radiation, and they would have given you that there, right? Ultraviolet radiation. Right? You could put back the same word, ultraviolet radiation. You also part C, well you have visible light. After visible light, as you're increasing in wavelength, you have infrared. I believe they give it that too here. Infrared radiation. And after that, you have the one with the largest, well in out of the options here, the one with the largest wavelength, which would be, well, they have microwaves. You could put the radio waves, right? Microwaves. Right? Well, I have radio waves there. You could have put that as well, right? Also, a common thing that you need to know is what are the light in the visible. Well, yeah. What lights make up the visible light here? So you need to remember Roy, G, Piv, right? And you need to remember what each of these letters represents. So R would be red, O would be orange, Y will be yellow, G will be green, B will be blue, I will be in indigo, and V will be violet. Just in case they have asked you, so you know list it. Right? Very important to note. Also, you need to recall the formula relating wave speed, frequency, and wavelength. So that will be V is equal to F lambda, where the wave speed would really be V, right? The frequency would really be F, and the wavelength would really be, we call as lambda, right? Very important formula to note. So if we make F the subject of the formula, we're going to have F is equal to V all over lambda. That is the wave speed divided by the wavelength. So we can say that F, the frequency, and the wavelength are inversely proportional, right? Inversely proportional. And by now you should know what inversely proportional means, right? Basically, if you're increasing in wavelength going to the right hand side, then you would be increasing in the frequency going to the left hand side, like down here, right? So you could draw arrow going like that. You're increasing going backward. That is in frequency. And you're increasing in wavelength going to the right hand side, basically. Right? Very important to know and understand that. Right? Okay, so yeah, microwaves could also put what it actually give you, which is really radio waves, right? Just to use back, you know what they give you. And that's how you fill out that there. Um, yes. So frequency will just increase in the opposite direction to what wavelength is increasing, to where wavelength is increasing. Right? Because they're inversely proportional. Now here you have state which sound wave parameters affects each of the following properties of musical note. So you have pitch. What is pitch? So pitch is directly related to the frequency of the sound wave. Right? So we can put that there. Is directly related to the frequency, right? Frequency of the sound wave, right? Very important to note. Um, so basically what this means is that I could put the remaining here, come down here. What this means is that higher frequency results in higher pitches, right? Obviously. And we could have kind of put well, they're proportional, in other words. Not really, but yeah, they're directly related in a way, like the proportional kind of way, right? Right? So on lower frequencies result in lower pitches, basically. Um, so what you need to know and understand too is a displacement time graph. Right? So let's say this is displacement here. Displacement. And here is time. Right? And let's see we have some waves here. So you start here and you go down there and then you come up, right? And then the waves kind of closer together here, right? Like that, right? So at this region here, because the waves are closer together, you have high pitch because they are, you know, kind of compressed, you could see, but closer together. And over here, in this region here, you would like have low pitch, right? Low pitch, right? When compared to the high pitch region. Why? Because we have a formula that relates period to frequency. So we know that frequency f is equal to 1 over the period. But what is the period? Well, the period is this distance here to this distance here. So in other words, this, right? This is the period. So if you consider this here now, this would be the T2. This would be T2. And this would be T1. Right? If you consider both cases, let's say this T2 is let's say this is 1, and let's say this T1 is 2. So if you had to find two different frequencies here, one is F1, you could have 1 all over T1 which is really F1 would simply be 1/2, right? And if you had to find F2, that could be 1 over T2, right? So F2 would really be 1 over 1, which is really 1, right? Um, so in this case, T2 gives a larger frequency, right? This over here, this gives a larger frequency of 1 because 1 is greater than a half. So frequency 2 would be greater than frequency 1 because you have a smaller period during the high pitch, right? Um, so so that's why you have high pitch over here, right? Because of the greater frequency, right? So that's important to understand. So when you want to talk about the pitch, you're really talking about the frequency. So it is directly related to the frequency of the sound wave, right? So what we could do now, we could explain loudness. So loudness is determined determined by the amplitude. This is the keyword that they're looking for. Amplitude of the sound wave, right? And if you come down here, I gotta put it over here, right? Let's see. So higher frequencies, okay, no, not frequencies. So it's determined by the amplitude of the sound wave. So greater amplitudes produce louder sounds, right? While smaller amplitudes result in softer sounds, right? Very important to note. Let's see. Let me show you. Well, let me show you the graph there for displacement versus position, right? Position, and this would be like displacement, right? So it would look something like, let's see, we put it in red, right? So that is one oscillation there, right? And this is another oscillation here. So basically, the amplitude is this distance here. So this is A1. A2 is, this is the other amplitude here. This is A2. As we can see, A1 is greater than A2, right? So at A1, you would expect to hear the sound louder when compared to A2, right? So that should be common A2 when compared to A2, right? Which would be softer because of the smaller amplitude, softer, right? So that's basically a wrap up of it there for the graphs And when you're explaining loudness, you want to talk about the amplitude. When you're talking about pitch, you want to talk about the frequency. Very important to note. Right, so let's go on to the next question here now, which is part C. They say a person standing 100 meters from a wall claps his hands and hears an echo 0.6 seconds later. Calculate the speed of sound in air. So a diagram will help with this. So let's say this is the wall here, right? This is the wall. And let's say this is the person over here, right? And the person claps, right? And let's say we have some sound waves being transferred here, right? Some sound waves. But actually, I want to say, the sound waves come up from the hand, and then it bounces off the wall, and then it come back to the person ears, right? For the person to hear it, right? Um, okay, pause. Right. Okay. So this process is reflection. So sound waves can be reflected. So reflection of sound waves. Right? So I'm gonna put the explanation here for you guys. Um, so sound sound waves can be reflected just like any other wave. Right? So sound waves can be reflected just like any other wave. Right? So smooth and rigid surfaces cause the strongest reflection. Right? Smooth and rigid surfaces cause the strongest reflections. Right? So the reflected sound waves are called echoes. Very important to note. I'm gonna put this in a different color. Right? The reflected sound waves are called echoes. Right? Very important to note. So in a case like this, we have to use our formula. That is, let me put it here. Speed is equal to distance divided by time. So a common error students normally make is that they just consider the 100 meter, right? But if the sound going to the wall, that is 100 meters. It covering, but it bouncing off the wall and it coming back to the person A, which is another 100 meters from the wall. So the total distance there is what you have to put in the formula, which will be 200, right? And this happens over a period of 0.6 seconds. So it took 0.6 seconds for the sound of the clap to go to the wall, reflect back, and come back to the person ears. So that asks us to calculate the speed. So the speed is equal to 200 divided by 0.6. And this will be measured in meters, this will be measured in seconds. You will get 333.33 meters per second. Right, so this would be the speed. This is your answer here. Right? I just put the diagram and them thing for you to understand it there, right? So what I could put up here too is that the sound wave traveled to the wall and back to the person. Sound wave traveled to the wall and back to the person, right? And all that has happened in 0.6 seconds, right? So the total distance is 100 plus 100, which is 200, right? So let me go on to part D, which is the last part for this question. Um, so let's see. So the question reads as follows. Figure 6 shows a plane mirror AB, right? A ray of light strikes the mirror at point X. You have a point X there with an angle of incidence between 0 and 90 degrees. I could say, it's like 45 degrees. I could put mine to be. So you might need a protractor for this. Complete the diagram to show the path of the incident ray and the corresponding reflected ray. Now notice they say reflected ray and not refracted ray. Notice they say mirror, right? Mirror as, reflection. Mark on the diagram the angle of incidence and the angle of reflection. In order to do this properly, you need to remember the laws of reflection, right? So what are the laws of reflection? So for any reflection at a surface, two laws apply, right? And the first law here will be that the angle of reflection is equal to the angle of incidence. So the angle of reflection is equal to the angle of incidence, right? Incidence, yeah. In other words, I with the hat is equal to R with the hat. Angle I is equal to angle R. And you can see this on the diagram, just now when I put it. And the second law, which is law 2, these laws are very important for you to remember and understand. So the incident ray reflected ray and normal are all in the same plane, right? So example, you have a flat mirror, which is the plane, shows reflection. So experiments show, well, you would have conducted this experiment in school, and it shows that the angle of incidence is always equal to the angle of reflection, right? Verifying the first law. So what you're going to have happening here is simply first thing first, you have to draw, which they will be looking for is the normal. That should be going through X, point X, right? Because that's the point at which the incident ray is supposed to be a straight line, right? But I don't have a ruler to draw that. So yeah. Anyway, so you have your angle of incidence. So what I did is I put this to be my angle of incidence. This has to be less than 90 degrees. So this will be I hat, which is the angle of incidence. So angle of incidence, right? This is your incidentary, right? And then you have your reflected ray, which comes out at the same angle. Well, it's supposed to be the same angle, so I just gonna kind of average it, something like that, right? So we just say that this is the angle of reflection, right? So put your arrows as well. This comes out, this goes in, right? So this will be the reflected ray, right? And this will be the angle of reflection, right? Very important to note. And the blue dotted line, well, you will call that your normal, and it will be at a 90-degree angle to the plane. So this is basically it here, and these are basically the steps in which you could carry out this explanation. So first is to draw normal, right, at x. The second one is to use protractor, right, and draw a ray entering, which you call your incident ray, x, right, with an angle between 0 and 90 degrees, right? And that's basically it there, right? So hopefully, you have a little better understanding of how to attempt these questions. If you have any questions, feel free to ask.